I'm Takahiro Yamazaki from Chiba University Hospital. Let's start my presentation. Introduction. There have been various reports on the biomechanics of plate fixation for distal radius fracture. Some studies have focused on the positioning of plate and screw, while others have examined the appropriate length of the screw. Here, we will focus on the length of the screw. Regarding screw length, a length of 75% of measured value is considered sufficient. Some reports suggest that even 50% of the measured value is acceptable. However, these findings are based solely on single-axial compression tests and have not been validated in different wrist positions. So our hypothesis is that optimal screw lengths vary depending on the wrist position. To examine whether the previous report screw lengths of 50% and 75% are truly appropriate and a clinically relevant loading condition in elderly patients. To explore the optimal screw lengths corresponding to various wrist positions, we use one fresh frozen cadaver upper limb for this study. CT scans were taken in various wrist positions, including neutral, 15 and 30 degree of volar flexion, 15 and 30 degree of dorsiflexion. We use mechanical finder version 30. For all cases, phantoms were employed to calibrate CT values. Cartilage was replicated by enlarging the ROI of the carpal bones. To create a fracture model, a wedge-shaped defect was introduced into the distal radius. The volar side was resected by 1 mm and the dorsal side was 10 mm, simulating an unstable fracture pattern that would require surgical intervention. The plate model was created using STL data from the Befecta plate, which is commonly used in Japan. This implant was developed by Dr. Matsuura, who is one of the most distinguished hand surgeons in Japan. We created 10 models by varying the screw length from 50 to 100% of the actual measured value in 5% increment. These 10 screw length models were developed for each of 5 wrist positions. The material properties are summarized on this slide. The bone property were calculated using Matsuyama's conversion formula. The cartilage property were referenced from previous reports. For the plate, the material property of pure titanium were used. Boundary conditions. We applied a total axial load of 300 Newton to all of the metacarpal bones. The proximal part of the radius and ulna were fully constrained. We evaluated the displacement of the distal fragment relative to the proximal fragment in each model and generate load displacement curve. We also assessed the failure load to determine the fracture strength. Results. Here are the results for the neutral model. This graph shows the load displacement curve for each screw length condition. This is 100, 90%, 85%, 80%, 75%, 70%, 65%, 60%, 55%, 50%. This graph shows the failure load for each model. If we set a cutoff value at 200 newtons, a screw length of at least 85% is required. Here are the result for the D50 model. The failure load for each model, a screw length of at least 80% is required. Here are the result for the D30 model. The failure load for each model, a screw length of at least 65% is required. Here are the result for the Vora 50 model. The failure load for each model, a screw length of at least 90% is required. Here are the result for the Vora 30 model. The failure load for each model, when setting the cutoff value at 200 Newton, it became clear that even 100 screw lengths may not provide sufficient fixation strength. Finally, when comparing the 100 screw lengths model across different wrist positions, we can observe that both stiffness and failure load vary depending on the direction of force application. Conclusion: the optimal screw length varied depending on wrist position. Even with 100 screw lengths, forceful activity in the volar flexion position should be avoided. In 30 degrees dorsiflexion, sufficient strength was maintained even with 65% screw length. Post-operative rehabilitation should encourage activity in the dorsiflexed position. That's all. Thank you for your attention.